Then there was a specific variation that we did, which was called the linear variation method, and I will also remind you of that because that was very interesting. So, on the subject of variation, this may not be required immediately, but it will be required at some point of time. So, the 3 is linear variation. So, I will first tell what is linear variation. Okay. So, linear variation is the following kind, that I actually choose my psi tilde, it is no longer arbitrary. I choose my psi tilde as a linear combination of some basis functions, So, let us call some Ci, okay. Now, that Ci do not confuse with this Ci, okay, obviously, some basis function Ci times chi I. Do not confuse these chi i's with spin orbitals, they are the basis for n particle function, n electron problems. So, these are n electron problems. So, I write my psi tilde as a linear combination of these chi I, where chi i's are known basis functions. So, what are my trial parameters? Ci tilde. So, basically what I am doing, I am changing this Ci tilde in a known basis and generating different psi tilde and then seeing what happens. Obviously, if my basis is complete, which means it is an infinite dimensional basis, then I go back to the theorem 1, Euler variation, which means I actually get exact solutions. Remember the Euler variation, the exact solution. I have already discussed such a case when these are determinants, full Ci. So, if I have an infinite basis and take all determinants, okay, then I will get exact solutions, which I already told you, full Ci, which will give you exact wave function, and here I will get, depending on the coefficients, all exact solutions. Okay, just that you do not get confused with this chi, probably I should use a different determinant, some di, okay, just to show that they are determinant. So, these di's are nothing but determinants generated out of chi. This can be one example, generated out of the one particle basis. Which is my chi's. It can be, this is an example, but it need not be. It can be any basis. But I am just trying to tell you that in case this is complete, then quite obviously I do not have to go through whatever I am telling you. You can directly go to the theorem 1, Euler variation, because then I am scanning psi tilde over the entire Hilbert space, because my di's form the entire space, and then quite obviously all stationarities of psi tilde H psi tilde will be one of the eigensolutions of H, which I actually mentioned without proof for the theorem 1. What is interesting, of course, is not that. What is interesting is that what happens when I do not vary over the entire Hilbert space, just like I did here a proof. What happens? Clearly theorem 2 would exist then, that whatever happens, this quantity would certainly be equal to E naught, right, greater than or equal to E naught. Again, assume psi tilde is 1. In many of the cases for proof, we will always assume the normalization, so do not worry. So, theorem 2 will obviously hold good, because that is greater than 1. Theorem 1 will hold good only if it is complete. Theorem 2 will always hold good. In case of complete, it will become equal to, otherwise of course, it will become greater than the exact ground state energy. So, then this is certainly holds good. Why am I talking of linear variation then, if it is just to tell you, highlight you theorem 1 and 2? No, there are certain more interesting results that we may get when we have a variation involving such basis, such linear combination of basis, and that is what I will first state. Again, without proof, I will first state, if you do this calculation of psi tilde H psi tilde, okay, assuming that again it is normalized, and do a stationary calculations. So, you analyze the stationarities of psi tilde H psi tilde. If you do that, then if this is a m dimensional basis or let us say k dimensional basis, okay, then first of all what I will get is that I will get k solutions. You will actually get an equation which I will show you later is a matrix equation in k dimensional space. In fact, right away you can now see that the configuration interaction that I discussed can be easily done using this for a incomplete set of determinants. That is, if I do not take all MCN, I take a few of them, then exactly this is going to hold good for configuration interaction because it is an incomplete set. So, if I have k number of determinants or k number of bases, again when I am saying determinants is an example, it can be any basis, then this will give me k solutions. That is very important first to note. How it will come to k solution I will show later. K solutions, and let me order those k solutions as E0 0 tilde E1 tilde E2 tilde etc., where this is less than equal to this. These are as far as the solutions are concerned. Remember, they are not exact solutions now because I have a k dimensional subspace, so they cannot be exact solution. Correct? So they are not of course exact solution, yet each of them must be greater than or equal to E0. That is also clear from the Rayleigh wreaths. Is it clear? Because theorem 2 of course holds in this case. So I order the solutions that I get out of the linear variation in this manner. What is interesting to note in this case is that obviously this E0 tilde, which is the lowest among the solutions, is going to be greater than E0, and all others are also going to be greater than or equal to E0, which is needless to say. But what is more interesting is that the second solution E1 tilde is also going to be greater than or equal to E1. And in fact, if I go forward, E2 tilde will be greater than or equal to E2 and so on. So all finally the Ek tilde would be greater than or equal to Ek. This is remarkable because now we are not talking of just greater than or equal to E0. Of course, if something is greater than or equal to E1 or E2 or Ek, it must be greater than or equal to E0. That is needless to say because E0 is the lowest. But now we are saying how much greater, that the second solution must actually be so much greater that it must be greater than the first excited state energy. The third one must be greater than E2. This is remarkable because now for the first time this bound that I said for E0 can now be changed to saying that I have an upper bound property for each of these E0, E1, E2, E3. Because many times in chemistry we are interested in excited states. So far my bound property was only for ground state, and now remarkably in the linear variation I have an upper bound property for excited states. So this is a very, very interesting problem. Again, this problem was, I had given that paper, I don't know how many of you have read this paper of MacDonald, Physical Review 1933. I don't remember the volume and page number, but you should be able to find out. It's a very, very nice paper by MacDonald, and actually this was expanded later by Hailerus and Undheim, and what I am going to talk is now called Hailerus. I hope all of you know Hailerus' name, yeah? Hailerus, Undheim, MacDonald theorem. Okay, that's the theorem that I am going to state. This is a part of the theorem. There are some parts of the theorem. So the first part is that each of the solution is greater than its corresponding exact solution. Exact solution. These are exact solution. The tildes are variational solutions. So I am using tilde for trial function as well as variationally optimized function. This is after variation. So from here I do a stationarity. That is important. Only after stationarity, whatever I get, they must all be greater than or equal to its corresponding exact solutions. Is it clear, this part? So this is of course much more powerful than just the Rayleigh statement, because Rayleigh statement only talks about being greater than or equal to E0. It doesn't say what solutions will be greater than or equal to E1 or E2. So here I can get the solutions. I will let you know how to get the solution, these k solutions. This is basically some matrix eigenvalue problem. But if you solve these, then whatever you get by stationarity, stationarity essentially means you expand this I tilde in this basis and make these Ci tildes stationary as the first order change of this becomes 0. So that is always the meaning of stationarity, right? First order change is 0. Do that calculus, you will get some results, and this is what you will get. Yes. That part is there. That I have not said no. Well, this part is correct. That I am going to come next, because this part doesn't say this. This part just says that each of them is greater than or equal to its corresponding state. So that is the next statement. Okay. That depends on how many states you have taken and so on. Okay. The part that he already mentioned is something that I am going to now talk about. Let me start from this k-dimensional basis and then add one more basis. So let me change the basis to k plus 1. I hope you understand the problem. So my trial function now becomes I equal to whatever 0 to, the solutions I have mentioned 0, I have made 1, but I think you understand what it means. So if I have to write, then this should be actually k minus 1 to be more correct, because it's a k-dimensional, so please make that correction. It can't have E0 to Ek. That will become k plus 1. Okay, I hope you understand that. That's fine. So I have now added one more basis. So my functions now become k plus 1 dimensional, and I will now get E0 tilde, E1 tilde, etc. up to Ek tilde. Now truly I will get up to Ek tilde. That's my k plus 1. Again, I ordered them in the same manner, that this is less than or equal to this, etc. E2 tilde and so on. What is interesting in this part of the theorem is, before I do that, let me just for sake of clarity say that I must distinguish this E naught tilde with this E naught tilde, because obviously they are different. So let me call these E naught tilde k plus 1, E1 tilde k plus 1, and so on. Okay. Then the theorem, this part of the theorem first says that the E naught tilde k plus 1 is always less than or equal to E naught tilde k. So in a k plus 1 dimensional basis, the corresponding solution that I am going to get after stationarity will be always less than or equal to E naught tilde with the previous basis. So adding a basis only lowers the energy. And you already know from the theorem 2, Rayleigh's variation principle, lowering the energy is very good, because it is bringing me closer and closer to the ground state. Now I know from here, lowering the energy is very good for other states also, because each of them is an upper bound. So each of them is coming very nicely closer and closer to its own excited states, to its own state energies, right? And so on. So I hope this part is clear. But please remember, when I compare this is an addition of one function. If you compare with a k-dimensional basis with another arbitrary k plus 1 dimensional basis, this is no longer true. This means that I must take this basis and only add one more. I can't change that basis. Then only the theorem is true. So if I add one more function, then all the numbers will decrease. All the numbers will decrease compared to the previous number, but interestingly, they will all be an upper bound. So they will never cross. So what does this together mean? So this is my E naught. Let me just do a simple calculation. This is my E1, this is my E2. Okay, and this is my E3. Let us say initially I do a 3-dimensional calculation. Okay, so I will get my E naught tilde somewhere here. I will have to get a E1 tilde, which must be higher than this, somewhere here. So this is my 3-dimensional. This is my 3-dimensional basis. I have total 4 solutions, and then I will get E2 tilde, which will be higher than here, but not necessarily here. Now that I don't have a fourth solution, this can go anywhere. Okay, this can go anywhere. But when it stops here, I don't care whether E2, 3 is here, in between E2, E3 or here. It has to be only greater than E2, right? However, let me add one more basis to this. Let me add one more basis to this. Then I will have my E0 tilde 4 here, which must lower. This must also be lower, and of course it cannot cross. This also must, this wherever this E2 tilde 3 will now also will actually come down, and this will come in between. What is interesting is it will come in between E2 and E3, and somewhere here we will go to this. So this is 4, or this is 3, of course, this is E2 tilde 4. Okay, and this will become E3 tilde 4. Again, it can go anywhere. This structure was ensured by a very interesting theorem that MacDonald proposed in that paper, and that is called the separation theorem. It says that between every two roots, roots means solutions, solutions to this problem, variational problem, lies one and only one exact solution. This statement is beautiful actually. It now means that when I do 4, E2 tilde 4 cannot be here. Initially I said E2 tilde 3 can be anywhere. It cannot be here because between these two roots there must lie one root, right? So once I do that, the last one can be anywhere, but moment I put another solution, that one will come down. So between these two roots, E0 tilde, E1 tilde, there is one root here. Between these there is one root, one exact solution. Between these there must be an exact solution. So this must not cross E3. I hope you understand. When I do a 4-dimensional basis, this cannot cross E3, exact E3, E2 tilde 4. So this must be below, because in between there must be a root, must be an exact solution. The root is of course the solution up to the variational problem. So lies one and only one exact solution, sorry, only one. This is actually the content of the theorem, which essentially says that nothing can cross its own root, because if it crosses, then also this theorem will be violated, because then between the two roots there will be no root. So essentially the variation method that I stated is actually a consequence of the separation theorem. What MacDonald did was actually to prove this theorem. Many times this is called interleaving theorem. Many places you might have it. Interleaving means essentially you understand what is interleaving. There are two leaves and in between there is one exact solution. So it's an interleaving theorem or separation theorem, and this actually comes directly from here. So for example, I go to a simple two root problem. So in a two basis, so I have E0, I have E1. So just to show, so this is of course E0 tilde 2, two basis problem. So this will be greater, it will be somewhere, and then there will be E1 tilde. The point is there must be one root between them. So that is the reason, if this is between E1 and E0, that is all you have to ensure, then of course the E1 must come here. So then this automatically becomes an upper bound E1. And then if I increase the basis, the next one will be automatically upper bound E2. So the upper bound property that I actually explained is a consequence of the separation theorem. Okay, and that is very most important thing. And obviously, when you add one more solution, they will also go down. There is no other option. So if you look at both these theorems, were actually put together in this content as a content of this interleaving theorem or a separation theorem, and this is what MacDonald has proved. This is basically a mathematical proof because essentially this solution come out, as I said, of an eigenvalue equation of a matrix, k by k matrix. So he only analyzed mathematically how these eigenvalues of a k by k matrix remain. That is nothing to do with quantum mechanics or quantum chemistry. Remember, this is mathematics. Eventually this will be an eigenvalue problem, which I will show. So it is only analysis of the eigenvalues of an eigenvalue problem. That if I keep on increasing the basis of an eigenvalue problem, how do the eigenvalues change? So it is actually can be applied to mathematics, physics, engineering, biology. In fact, engineering people have applied a long back. But it is very interesting that this application immediately after McDonald's thing came, almost immediately came to quantum chemistry, very fast. Because the quantum chemistry was developing, and in particular, of course, you can imagine for this problem of linear variation, which is basically configuration interaction. I already told you that if I make a linear combination of a determinant, then I have a configuration interaction. So to the CI problem, this will be actually used. And I have not told you, of course, how to get the CI tilde, neither in the context of CI nor here, but that will be the matrix eigenvalue problem, which I just promised I will come to that very quickly. So that essentially is the content of the linear variation method, and as you can see, it's a very powerful method, because if I do an arbitrary variation of Rayleigh-Ritz, I really don't know where I stand. But here, I have a lot more idea of where I stand. I also know that this solution cannot exceed this. It must be, because there has to be separation, interleaving one root. So that is a very one exact solution. So that is why the linear variation is a very powerful method in quantum chemistry. Again, lot of problems, linear variation is used. For example, the particle in a box, just now I gave an example. C mn x to the power m x minus l to the power n. That's a linear variation problem. Please understand. Except that the basis is not normalized. Please remember, my basis is normalized. I have to again mention here. So it will not be an exact eigenvalue equation there. There will be some kind of a change, but basically it's not very difficult to renormalize. You can always go to a renormalized basis, which is orthonormalized from there, and then do the problem. So if they are normalized, then the solutions come out very nicely. And this will be the content of how to get the solutions in any of the linear variation. And I will just show, I have 5 or 10 minutes, I will actually show that how these case solutions turn out to be an eigenvalue equation, so that I complete this part of the variation method. Okay? I think I am not going to discuss too much about variation method, because next class I want to go into the actual Hartree-Fock method, okay? Hartree-Fock theory. All right. So I come back to this linear variation very quickly and tell you now how to get the solutions. And because I have been talking of the matrix, so we must know. So what do we do? A simple way. So basically, what we want to do is to find out the average value of psi tilde a psi tilde. The first order change should be equal to 0. So that is basically the content of the variation method. So I must put this here on psi tilde on this side, psi tilde on this side, and make them equal to 0. To do that, of course, I must ensure that the di's are normalized. Okay? So if I do this, let's write down the Lagrangian, which I am subject to this condition. So what will be the actual statement? That this minus sum ij lambda ij di dj minus delta ij, right? So this is what is called the Lagrange variation. I hope all of you know this is the variation under constraint. So I am varying this under the condition that di dj minus delta j should be 0. I think I have done this many times. So this is what I am actually going to vary. So I am going to vary the Ci tildes, yeah, I can keep it like this. I am going to vary the Ci tildes such that this quantity becomes 0. The first order change is 0. So let's do it very quickly, how the first order change becomes 0. So let's expand the psi tilde. I had already done this expansion once in proving the Rayleigh-Ritz variation principle. So it's the same thing, sum over ij Ci tilde star or whatever Cj di h dj. Note that That time I had expanded in terms of exact eigenfunctions for proving the Rayleigh-Ritz principle. Here it is not an exact eigenfunction, they are basically the bases. So this is what I will get here. I expanded this as I, this as j, so I get di h dj minus sum over ij lambda ij di dj actually this is not right. Actually this is not right. Di dj's are anyway orthonormal. It is a ci square, sorry, mod ci square minus 1, that is equal to 0. Okay, so it should be ci star ci minus 1 into lambda ij. Okay, because obviously I told you that if these are orthonormal, essentially the condition is that this must be, square of this must be equal to 1. Okay, so ci star ci. All right, so now what I do, I vary ci star, first order variation, and then find out what is the change. Or I can actually differentiate this expression with ci tilde star. Either way it is okay. So if I do this differentiation, again of course if I put this, then there is only one condition, I do not need to write lambda ij, I can simply write this, sorry, there is a mistake here in the very first place. So I can simply write as a lambda, because there is only one condition, mod ci square equal to 1, so there is only one Lagrange parameter. Okay. So now if I vary with respect to ci star, what will you get? You will get Cj times di h dj. Note what I am doing is, this is my Lagrangian, I am varying this Lagrangian with respect to delta ci star. Either delta ci star or delta ci, does not matter, only one of them. So you have a sum over j, Cj di h dj minus lambda times, this is sum over I, okay, this is sum over I, lambda times ci equal to 0. It is very easy to do this, because lambda time 1 will not contribute anything. When I do ci star ci, one of the summation is ci, so I differentiate, only ci will remain. Here there is a double summation, so when I differentiate ci star, Cj will remain with a single summation. So the entire thing will now become di h dj times Cj, sum over j, equal to lambda times ci for all I, because I have to differentiate for all I. Okay, so I am sorry for this little mistake here on the constraint, so that is why there is a little confusion. There is a sum over I, ci star ci minus 1. So that is, and there is only one condition, so I need only one parameter. This obviously, as all of you can recognize, is a matrix eigenvalue equation. You construct this element, matrix element, and call, these are numbers, right? So call this as a matrix. So you arrange them in the row I, column j. So it is a two-dimensional matrix, because when I integrate this basis Hamiltonian with this basis di star dj, I will get number for each ij. So eventually this is a matrix equation. So it is a d, let us say hij or whatever I call it, Cj equal to lambda ci. So let us call this matrix as a hij. So this will then become sum over j, hij, Cj equal to lambda ci. And all of you know that this is basically a matrix eigenvalue equation. So that is a matrix. This is the column of C's which I am trying to find out. This is the column of C's that I am trying to find out, equal to the eigenvalue times one number. And this is for all I. So obviously I am going to generate the full set, and then you have to solve this equation. So this is how you actually get these k solutions. Obviously if I have a k by k matrix, how many eigenvalues are there? K eigenvalues. Again, all of you know from the mathematics. So if I have a k by k solution, I get k number of lambdas. I have written this equation for one lambda, but you have actually k number of lambdas, and eventually these coefficients can become a square matrix, and I can write a different form. And I have shown this also, how to write matrix eigenvalue. So matrix eigenvalue equation is very important. Please read it, revise it. So one of the revision point, those who are revising, must be matrix eigenvalue equation properly. We have done this very thoroughly. If you do not understand matrix eigenvalue equation, it is very hard, because it will keep coming in quantum chemistry in different forms. Okay. So the CI problem that we have been discussing, which is basically linear variation, is nothing but solution finally at the matrix eigenvalue equation. All you need to do is to calculate these matrix elements. The matrix element of the physical Hamiltonian in the basis, whatever is my basis, okay, and then diagonalize that matrix. Okay, so that is basic recipe to get all the solutions, and this particular way of writing, the way I wrote here, expanding psi tilde and psi tilde left right like this, is something that I showed for Rayleigh-Ritz principle, but there of course these were exact eigensolutions. That was a formal basis, formal expansion to show that the upper bound theorem with respect to E naught. Here it is a basis, so of course these numbers have to be computed. These are not the eigenfunctions of the Hamiltonian. Please remember, I again repeat, many people get confused. These are any basis. So obviously these are not eigenfunctions. If these are eigenfunctions of the Hamiltonian, I would not do this. My D's are already eigenfunctions, right? So I expanded that time psi tilde in terms of eigenfunctions only to show the upper bound principle. Of course, I don't know the eigenfunctions. So these are some bases in which you calculate this matrix element and then solve an eigenvalue equation. And then you will get all the case solutions of the linear variation problem, and they have this property that I mentioned, the separation theorem. Each of them is an eigenfunction, is upper bound to its own exact solution, corresponding exact solution. And of course, if I increase, they all change values, they all become lower and lower. So entire content is what is basically given by the separation theorem. I think with that we will leave the variation method. Now we are going to apply the variation method to the derivation of the Hartree-Fock. Okay, Hartree-Fock equation. All right, so I think we'll close the class today.